In this video, I will walk you through FRQ 5 from the 2021 AP Calculus exam. This problem is primarily about implicit differentiation. If you appreciate the content, please give it a like. Consider the function y equals f of x, whose curve is given by the equation 2y squared minus 6 equals y sine x for y greater than 0. Part A, show that dy dx is equal to y cosine x over 4y minus sine x. To make dy dx show up, we are going to take the derivative of both sides of this equation with respect to x, term by term, starting with 2y squared. For every term, I'm going to use the chain rule, even for this term right here. So the outer function, the derivative of the outer function is 4y, but then the inner function is y itself. And according to the chain rule, you multiply by the derivative of that inner function, which is dy dx. The derivative of a constant is 0, so that is gone. When we get to this part, we are going to have to use the product rule. We have this yellow function times the blue function. The way the product rule works, you go through it twice. The first time through, you take the derivative of the yellow function, which is dy dx, and you leave the blue function unchanged. So I'm going to bring down the sine x. Then you put a plus, and you go back through it again. The second time through, you leave the yellow function unchanged, so I bring down the y, and you take the derivative of the blue function. The derivative of sine x is cosine x. If I try to do the chain rule, I would multiply by the derivative of the inner function, but that's just x. And the derivative of x with respect to x is just a 1. So we've taken the derivative of both sides. Our goal is to find an expression for dy dx. So we need to get all terms that involve dy dx on the left side of the equation and leave everything else on the right side. So basically I'm going to subtract this term from both sides to move it over here. Now we have this. The point of putting all of the terms with a dy dx on the same side of the equation is so we can factor out the dy dx as a GCF outside of parentheses. So I'm going to put the dy dx in the front, and then consider what will be left behind inside the parentheses. That's going to be 4y minus sine x. And then that is equal to y cosine x. We can get dy dx by itself by dividing both sides of the equation by this expression. So basically, this set of parentheses will end up in the denominator. Dy dx is equal to 4 cosine x over 4y minus sine x. And that's exactly what we were supposed to show. Part B, write an equation for the line tangent to the curve at the point 0, radical 3. We always write the equation of a tangent line in point-slope form, so we know we're going to need a point and the slope. Well, they gave us the point. The point of tangency is 0, radical 3. We just need to find the slope at this point. In calculus, we know the slope will be given by the derivative dy dx. Now, don't go plugging in x and y all willy-nilly. You need to use proper notation like this to show that you are about to evaluate dy dx at 0, radical 3. Once you've written this vertical line and the 0, radical 3 point at the bottom, now you can start plugging in 0 for x and radical 3 for y. Now we have this. We just need to evaluate cosine of 0 and sine of 0. Cosine is the x value on the unit circle, and at 0 radians, the x value is 1. So radical 3 times 1 is just radical 3. Sine is the y value on the unit circle, and at 0 radians, the y value is 0. So this term is gone. So we have this. We notice that the radical 3's will now cancel out, leaving behind 1 over 4. So 1/4 is the slope. Once we have a point and the slope, we can write the equation of the tangent line. It goes y minus y, so that's y minus radical 3 is equal to the slope of 1/4 times x minus x, so that's x minus 0. You can write your final answer like this or like this. Part C. On the interval from 0 to pi, and for y greater than 0, find the coordinates of the point where the line tangent to the curve is horizontal. Hopefully you have memorized that a horizontal tangent line means the derivative is equal to 0. We know that dy dx is equal to this rational expression, this fraction, and a fraction is equal to 0 when the numerator is equal to 0. So dy dx will equal 0 when y cosine x is equal to 0. We can find possible solutions to this equation by setting each factor equal to 0 separately. That's y equals 0 and cosine x is equal to 0. We can throw out the y equals 0 as a potential solution because y is always greater than 0. It is a given limitation. Cosine is the x value on the unit circle, and on the interval from 0 to pi, cosine is equal to 0 at pi over 2. So that's the solution to this tiny equation, x equals pi over 2. When they say find the coordinates, they mean find the x and y coordinates. So far we have found the x coordinate where the tangent line is horizontal. How do we find the y coordinate that goes with an x coordinate? You have to plug it back into the original equation given in the setup. Again, don't just immediately plug in the pi over 2. You always have to indicate that you are evaluating at a specific value. You can do that with the phrase at x equals pi over 2. You are now free to plug in pi over 2 for x. Sine is the y value on the unit circle, so the sine at pi over 2 is 1. And y times 1 is just y. Let's get 0 on one side. I see some factoring in our future, so let's subtract y from both sides, and we get 2y squared minus y minus 6 is equal to 0. This is hopefully factorable as a binomial times a binomial. 2y squared is factorable as 2y times y. The number 6 can either be factored as 2 times 3 or 1 times 6. We will not put the 2 here and the 3 here. We're doing a little bit of trial and error. If there's no common factor in the original trinomial, there will be no common factor within the parentheses either. So it's not going to be 2 and 2. So I'm not going to waste my time with that experiment. Instead, if I want to try the pair of 2 and 3, I will immediately put the 3 here and the 2 here. The phrase I use to factor is inner plus outer must equal middle. When I say inner, I am talking about these values. Inner is 3y. I normally do this in my head. This is just for instructional purposes. So inner, I have 3y. Outer, I'm talking about the product of these two. So outer, I have 4y. Inner plus outer must equal the middle. This is what I mean by the middle, negative 1y. We can make negative 1y if we have a, let's see, a positive 3y and a negative 4y. That means positive here and a negative here. Also, positive 3 times negative 2 is negative 6. So, ta-da, we factored it. We can solve this factored equation by setting each factor equal to 0 and solving. Setting this factor equal to 0 will lead to y equals negative 3 over 2. We subtract 3 and divide by 2, so kabam! Setting this factor equal to 0 gives us y is equal to 2. Of course, we need to throw this potential solution out because we have the restriction that y must be greater than 0. So we are to disregard this one, which is less than 0. So we have the x-coordinate and the y-coordinate of the point where the tangent line is horizontal. Let's give it a nice clean summary statement. The tangent line is horizontal at pi over 2, comma 2. Part D. Determine whether f has a relative minimum, a relative maximum, or neither at the point found in Part C. Justify your answer. We have learned two ways to identify the location of a relative max or min. One is called the first derivative test, and the other is the second derivative test. For the first derivative test, we make a y prime sign chart and look for sign changes. For the second derivative test, we evaluate y double prime at the places where y prime is equal to 0. In other words, at the locations of horizontal tangent lines. But only one of these will work in this particular situation. You cannot make a y prime sign chart when your y prime is a function of y and not just x. So the first derivative test is out. Second derivative test it is. We need to find the second derivative by taking the derivative of the first derivative. Since this is a quotient, we are going to need the quotient rule. The little poem for the quotient rule goes low d high less high d low. Draw the line and down below, the bottom squared will go. The bottom squared is 4y minus sine x squared. Now, what was the rest of that again? Low d high. Low means copy down the denominator. 4y minus sine x. D high means the derivative of the numerator. But this is going to require the product rule. We have the yellow function y times the blue function cosine x. So to take the derivative here, we are going to have to go through this twice. The first time through, we take the derivative of the y, which is dy dx. And we leave the second function unchanged, cosine x. And we put a plus. Then we go through it again. The second time through, we leave the yellow function unchanged, and we take the derivative of the blue function. The derivative of cosine x is negative sine x. So I'm going to put the sine x right here. By the way, when you need to multiply by negative sine x, don't do this and put the negative right here in the middle. Students will very often try to do this, but then they'll end up doing subtraction instead of multiplication. So instead of doing this, I want you to take that negative sign and put it in the front of its term. Right here. Make sure you put parentheses around all of this product rule business because we do have more than one term. Without parentheses, it is wrong. So this is low d high. Less means subtraction. And now it's high d low. High means just copy down the numerator, y cosine x. D low is the derivative of the denominator. The derivative of 4y with respect to x is 4 dy dx. And I'm just going to bring down that minus sign. The derivative of sine x is cosine x. Make sure you put this in parentheses because it is more than one term. Without the parentheses, it is wrong. So this is low d high less high d low. This is an expression for the second derivative. The next step is to evaluate the second derivative at the point found in part C, the point pi over 2, comma 2. Use proper notation. Put a vertical line, and at the bottom, put your pi over 2, comma 2. Now we can substitute pi over 2 for all the x's and 2 for all the y's. But there's one more very important thing I need you to be aware of. The second derivative test only works when dy dx is equal to 0. We can only use the second derivative test on this point because we know there is a horizontal tangent line at pi over 2, comma 2. We know that at pi over 2, comma 2, dy dx is equal to 0. This is always true when you are doing the second derivative test. So, as you gear up to do the second derivative test, know that dy dx is going to equal 0. It has to. This fact is going to simplify our work quite a bit because any term that has dy dx in it is going to be 0. So here I have plugged in pi over 2 for all the x's, and I plugged in 2 for all the y's, and I plugged in 0 for dy dx. Notice that cosine of pi over 2 is 0. That's at the top of the unit circle where the x-coordinate is 0. So this and this will be gone. Right? Cosine pi over 2 is 0. So all of this gets wiped out. Also, the sine of pi over 2 is 1. Plugging in 1 for the sine of pi over 2 and 0 for the cosine of pi over 2 gives us this. That's 7 times negative 2 over 7 squared. Hopefully you can already tell that this is negative, which is all that really matters. But just for fun, this 7 will cancel out one of these 7's. So this is negative 2 over 7. Again, all that really matters is that at the point pi over 2, comma 2, the second derivative is negative. Before we write the answer and justification, here's a quick review of how the second derivative test works. First of all, it only works when the first derivative is equal to 0. So we made sure to pick a point where dy dx is equal to 0. Where the first derivative is equal to 0, the curve has a horizontal tangent line. So that might look like this. You can see there's a horizontal tangent line right here. And that would be a relative max. But it could also be like this. You know, a horizontal tangent line could be at the bottom. But it could even be neither a relative max nor a relative min. Like imagine that we had a point of inflection. This also counts as a horizontal tangent line. That's why we need more than just dy dx equals 0. This second part, where we know the second derivative is negative, that tells us that the curve is concave down at the point in question, which means we can forget about these options, and it must be this option. Therefore, the curve has a relative max at the point pi over 2, comma 2. When we write the conclusion in a moment, we need to include both of these facts. Notice they have named the curve f. So be specific. Don't say the curve or the equation. Say f. F of x has a relative maximum at pi over 2, comma 2 because blank and blank. I always put these blanks in here for a moment to emphasize to you that the second derivative test always has these two parts to it. The first part never changes. It's always that the first derivative is equal to 0. So dy dx equals 0, or sometimes it's f prime equals 0, or y prime equals 0. This is the second derivative test, and the second blank is where the second derivative comes in. This is where you say the second derivative is negative, or sometimes it'll be positive. Because the second derivative was negative, we knew the curve was concave down at pi over 2, comma 2. That's how we knew that f of x has a relative max at this horizontal tangent line. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.